In electrostat, we now turn to applications of Gauss law. Actually, in practically, there are multiple applications of Gauss law throughout the electrostats up to any level. But in our syllabus, we are confined to finding electric field through certain charge arrangements. We know very well that if we have a point charge, then due to this point charge, the electric field at any point P is given by Q by 4 by epsilon R square. Right? This is for point charge. But if there is collection of charges, there could be a line charge, there could be charge on surface. In that case, we need to perform, there are two ways to find. Either perform integration, that becomes too much mathematically complex. Gauss law makes it tremendously simple. But there is just one condition for that. The charge arrangement, if it is symmetric, then application of Gauss law is simple. If charge distribution is not symmetric, still we can apply Gauss law, but it will become again complex. So here we will be talking about the symmetric charge distributions. First of all, electric field due to line charge. This is line charge. A wire theoretically is composed of infinite length from both sides. Right? It has charge per unit length. It is lambda. Lambda is charge per unit length. Now, suppose we are interested to find electric field at this point, which is at distance r from perpendicular distance r from this wire. What I do here, I draw a line in this way. I'll make a cylinder again. Here, this cylindrical surface is hypothetical, and it is called Gaussian surface. So, first of all, the need is of a Gaussian surface. Gaussian surface is selected in this way that the charge distribution is symmetric with respect to that surface. Now, this straight wire can be symmetric for a cylinder. Now, if it makes the axis of the cylinder, right? This cylinder has three surfaces. This S1, this S2, and this curved surface S3. I hope you know vector area is a vector quantity. The top surface will have area vector in this direction, bottom one downwards, and the peripheral that will be radial from the wire. You can see in this way for this S3. I draw. This is the wire. This is the direction of area vector. This is the way. This is the overall. This completely. This is. Now, we consider the length of the cylinder. Suppose it is L. This is P. This length is L. And this surface area, this radius, this distance is R. Now, let's calculate the values of S1 pi R square, S2 pi R square. Let's see S1, S2 is equal to S. Right? S3 is this curved surface area 2 pi r. These calculations will help us a lot. Now, first of all, let's see the charge enclosed. Alright, Q enclosed. Look, charge per unit length is lambda. The length L is enclosed by this cylinder. So, this is charge per unit length. Charge enclosed becomes lambda into L. Now, as per Gauss law, E dot ds over the closed surface Q enclosed upon epsilon. This is the statement of Gauss law. Now this is for the integration is for closed surface. I make it for E dot ds over the closed surface. E dot ds for S1, E dot ds for S2 plus E dot ds for S3. Now, to apply Gauss theorem, two things are required. The Gaussian surface should be symmetric about the charge distribution. Secondly, we must have the idea of the direction of the electric field due to that charge distribution for all the surfaces. Now, look here. From this positive charge, the lines of force will be like this, the radial, right? This is the line charge, lines of force will be like this, right? For this surface, S1 and S2, the area vector is in this direction and lines of force are in this direction, which are 90 degrees. At this position, this is electric field, this is S1. At this position, it is electric field, this is 90 degrees. And at the periphery, at the curved surface, at each point, the direction of E and direction of S are same. So at first, if I move further, this is E dot ds for S1, E ds cos 90 plus for S2, E ds cos 90, this is S2. And lastly for this one, we have E ds cos 0. Then automatically this term, these two terms become 0. And we have E dot ds is equal to E ds curved surface. Now, E integration will be only of ds. I write here E ds for S3. This curved surface has area 2 pi RL. Right? It is what? E dot ds over the closed surface. Another statement, actually the basic statement of Gauss theorem is what? E dot ds over the closed surface is equal to Q upon epsilon naught, means E dot ds is equal to Q enclosed upon epsilon naught, and here we have got E dot ds over the closed surface E into 2 pi r L. Definitely these two must be equal. E into 2 pi r L Q enclosed upon epsilon naught. E equals to Q enclosed was lambda L 2 pi epsilon naught R L. L cancels. We have finally E is equal to lambda upon 2 pi epsilon naught. The direction of this electric field is radial at every point. So in vector form, it can be written as lambda by 2 pi epsilon naught r cap. This is the electric field due to the charged wire. Now, we come to another application. E due to uniformly charged non-conducting sheet. Look, I have this sheet of charge. I want to find electric field at this point B. This sheet of charge has charge per unit area. As I told you before, that was linear charge. Charge per unit length was calculated. The charge is on surface. Charge per unit area is calculated. Here it is sigma. Now, the important and intelligent thing here is to select the Gaussian surface. We still have the same formula, that E dot ds. What I do here, I consider cylinder like this. This surface is S1. This is S2. Again, this curved surface is S3. Further, it's plain sheet like this is plain sheet, right? The electric field will be in this direction, and from here it will be in this direction, right? Charge here in this direction, here in this direction. So for this condition, for S1 and S2, angle between E and area vectors are 0 degree, because here electric field will be this, here it will be this. Definitely for S3 it becomes 90 degree. Now I calculate charge and close. Before that, I take S1 is equal to S2 is equal to S. Definitely the magnitude of these two areas will be same. Now I calculate charge enclosed. Q I call sigma into S. Charge per unit area into area. Now I apply E dot ds Q upon epsilon naught. E dot ds for S1, E dot ds for S2, E dot ds for S3 is equal to Q by epsilon naught. S1, S2. These become E S cos 0 plus E S cos 0 plus E S cos 90 Q by epsilon. This term becomes cos 90 0. This is ES, this is ES. I have 2 ES Q by epsilon naught. Here I have 2ES. Q by epsilon naught. Q is what? Sigma S upon epsilon naught. Finally, I have E is equal to SS cancelled sigma by 2 epsilon. There is a little confusion always between the students, the sigma by 2 epsilon or sigma by upon epsilon only. I will explain it in the next derivation. Here I have taken non-conducting sheet. That is one layer of charge. You can consider it as a one layer of charge. Right? Now let's come to just the near derivation of this. It is what? E due to a conducting charge. E due to a conducting charge plate. This time I'll take some thickness of metallic plate. Conducting means metallic because here is some charge Q. Here the assumption of Gaussian surface is to be taken to be intelligent. Here I take similar cylindrical surface. It goes here. Now it goes inside. Here the charge density is sigma. This surface again S1. This is S2. This is S3. And very clear that S1 and S2 are same S. And now Q enclosed sigma S. I do the same thing E dot ds over the closed surface Q upon epsilon naught. E dot ds S1 E dot ds S2 E dot ds S3 Q by epsilon naught. Now, for S1 and for S2, the electric field, look here. Interesting thing is that at this S1, there is some electric field and angle is 0. I write ES cos 0. Inside the metal, the electric field is always 0. This is a fact, I'll explain it later. But inside the metal, it is, I write E in is 0. There is no question of angle, actually E is itself 0. For the third surface, the angle is 90. It is ES cos of 90 is equal to Q by epsilon naught. It is ES cos 90 0 Q by epsilon naught. Q is what this sigma is. E is equal to sigma upon epsilon naught. Now look the difference. There was sigma by 2 epsilon naught. Here it is sigma by 2 epsilon naught. There is another way also to understand this, how it does happen. We'll discuss in case of capacitors. Then there will be discussion of parallel plate capacitor. Then we will discuss about this. Now, fourth application. E due to uniformly charged, non-conducting. Again, I am making stress over it. Non-conducting sphere. First of all, understand the situation. Here is the sphere, non-conducting, then charge can reside inside. Again, I'm saying, if you give charge to any matter, it comes to the surface. Again, I'm telling you that I'll explain the capacitors. Why does it come? Because you can just take a, I can give you just a simple hint for it. Charge can be moving, it's conducting. It can move from one place to another place. We have any shape of, suppose, any shape of metallic body. You give some charge, I say you put 2 electrons. They're free to move. Then according to the basic principle of nature, every system wants to gain stability. And to gain stability, it wants to minimize its potential energy. If two negative charges are very close to each other, then they're repelling their potential energy maximum. Now they'll try to be maximum apart. So they'll move as much as apart possible. Now if there are n number of electrons, they will also try the same. So the final destination possible for them, it said the minimum possible energy which they can acquire in the given situation. So all electrons or all the positive charge will definitely come out of the surface. It will come on the surface. It cannot reside inside. But for a non-conducting surface, non-conducting object, like you can take a thermocol ball, a ball of made resin, right? There, the charge is not free to move, so it will remain where you have placed it. Now, there is its radius is say r and charge is q. Then q is equal to 4 by 3 pi rq. Or I say 3q by 4 pi rq. This is denoted as charge density. Now you are introduced with all three. This is lambda, sigma, rho. Lambda charge per unit length, or we say linear charge density. Sigma charge per unit area, we say surface charge density. Rho charge per unit volume is called volumetric charge density. Now, this is rho. We are interested to find electric field. This point is O, this point is A, this point is B, this point is C. Here, the electric field is supposed to find it A, which is inside, R is less than capital R. OB is equal to R is equal to capital R. OC is equal to R greater than R. This point is inside, this is on the surface, this is outside. These three discussions will carry out. Now, first of all, I talk about E at A, inside the point. Okay? Let OA is equal to R. Now, I assume a spherical Gaussian surface. Spherical Gaussian surface of radius r, right? Say S vector. Of course, magnitude of vector S will be 4 pi r square. It will be a sphere of radius small r. Its area is 4 pi small r square. Now, E dot ds q enclosed open epsilon. Here, I come to find q enclosed. It is charge per unit volume into this volume 4 by 3 pi small r cube. Later I will come to this. E dot ds. At this point, I told you that to apply Gauss theorem, we must have symmetry once. Secondly, we must have idea regarding the direction of electric field. Right? At this surface, the direction of electric field is radial everywhere. So angle between E and S is 0 degree at each point. So here I get E ds cos 0. Q enclosed, I write only this upon epsilon naught. Now, another point, these distances are R, E is same everywhere. Integration of ds. Integration of ds will get this area 4 by R square is equal to Q enclosed. Q enclosed rho 4 by 3 by R cube upon epsilon naught. Further I take calculations here. Look, 4 pi cancelled. From square cancelled. I have E is equal to rho R upon 3 epsilon naught. In vector form, I write R cap. This is a fantastic relation. Magnitude of E is proportional to R. Interestingly, as we move from O to the surface, the electric field goes on increasing. We'll discuss about the graphs. Then you will enjoy this. And now, second point, E at surface means point B. Now I just make change. This OB will become capital R. And this will become capital R. Everything going same here. Just a little change. Here it is E into 4 by capital R square. Q enclosed rho 4 by 3 pi R cube upon epsilon naught. 4 pi cancel. Now I have again E is equal to rho R cube upon 3 epsilon naught capital R square. At surface, small r is what? Capital R. And now it becomes E is equal to rho R upon 3 epsilon naught. It can be written in another form also. You will definitely prefer that form. And that's a very commonly used. E is equal to rho R upon 3 epsilon. What is rho? 3q by 4 by R cube. 3q by 4 by R cube into rho R upon 3 epsilon. 3 cancels. This cancels. Rho is Q. This is Q upon 4 pi epsilon naught R square. Right? Now we turn to the last point, the point outside, point C. E at C, outside. E dot ds. Q enclosed if I take Gaussian surface in this way, then Q enclosed is total charge directly rated upon epsilon naught. This OC, if I take OC is equal to R, then at each point direction of E and area vector is same, so it is E ds cos 0 q by epsilon naught area 4 by r square q by epsilon naught p is equal to q by 4 by epsilon naught r square. This is an interesting result. For the outside point, this sphere behaves as a point charge placed at center. Or we can say in other words, that the whole charge can be supposed to be concentrated at the center. It is like a point charge placed at this point, q by 4 by epsilon r square. In vector form, this becomes exactly like point charge. Right? This is for a uniformly charged, non-conducting sphere. Now there is a last derivation according to your NCERT syllabus. That is E due to a conducting sphere is a sphere conducting. Now it is metallic. So the whole charge will come out on the surface. I counted Q. There is point O, there is point A, point B, point C. All now clear. This is radius R. First, E at A, inside. OA is equal to R. I assume here a Gaussian surface. Actually, the whole charge is on the surface and we are inside. There is no charge inside? No. E dot ds Q enclosed upon epsilon naught, but here Q enclosed is 1. This is 0. So E dot ds is 0. However, ds area is not 0, then we must have E 0. Yeah, I should say E inside a metallic surface is 0. Keep in mind, it's a very simple statement. Inside a metallic surface, electric field is 0. Now, we come to point B. E at B. E dot ds by this sphere itself becomes the Gaussian surface. Charge enclosed is Q upon epsilon naught. At each point it becomes 4 pi r square Q by epsilon naught. E is equal to Q by 4 pi epsilon naught r square. Lastly, E at C. Point C is outside. Again, let OC is equal to R, and this is the Gaussian surface. E dot ds. Now it's very clear in this surface the charge enclosed is same, Q upon epsilon naught. E dot ds. E ds cos 0 everywhere. Q by epsilon naught. ds surface area is 4 by small r square. Q by epsilon naught, and finally I have E is equal to Q by 4 by epsilon naught r square. In vector form I write here, then it will be in this radial direction, I say r cap. Here also it will become r cap. Right? This is about the metallic sphere. These are the derivations given in your NCERT syllabus. And these are the applications of Gauss theorem. Now, let's talk about the graph. I told you, graph of a non-conducting sphere electric field, right? And that's very important actually. So I'm discussing about its graph. Look, this is a non-conducting sphere. This is I'm taking R. This is E. Okay, this is symmetric here, just so that you can easily understand. At this point, electric field is 0. From inside, E was proportionate to R. At this point where R equals to R, it goes on straight line. After that, here it is proportionate to R. Outside, it is proportional to 1 by R square. It is 1 by